Thank you very much, Danuta, for this kind introduction. Can you hear me okay? Can you see the slides now?
We can hear you and we see the slides.
Okay, thank you so much. I also want to thank you for Gianni for the kind of invitation and Darius for organizing these events. You guys keep the scientific communication still alive during such a difficult pandemic time. And specific for us from North America, this is a wonderful opportunity that we could actually keep communicating with colleagues in Europe and other parts of the world as well. The past few, the rounds of the webinars, I've learned a lot from the colleagues. And today, I would like to share our research, as Danuta mentioned, about MRI contrast agent, but this is not gadolinium-based contrast agent, but rather based on a manganese porphyrin. And I will talk a little bit about our recent discovery and how we try to understand these unusual but very interesting behavior of manganese porphyrin as MRI contrast agent, and talk about the limitation of the classic model and what we can do, the future opportunity of using those manganese porphyrin. So as you have learned a lot already from the previous speakers regarding the gadolinium contrast agents, so the concept of using paramagnetic species to enhance the proton in the MRI relaxation is quite actually a concept that is back in a few decades before the discovery of MRI, the technique of MRI. So it's not surprising that when the first paper published in 1973 by Lauterburs in Nature, he already, in the very first MRI image, he already using the paramagnetic species. In this case, he was using manganese sulfate to show that the enhancement of the MRI relaxation could lead to the increase of the MRI signal. And once this MRI concept was published, and the technique was quickly being recognized by the medical community, and very soon this technique was get more widely applied. So in the early 90s, in the early 80s actually, the field of the contrast agent used paramagnetic species to enhance MRI signal are getting increasingly popular. And wide areas of these paramagnetic species, such as iron-based or chromium-based even, and even nitric oxide, those kind of organic radical, as well as oxygen, has been recognized as a potential paramagnetic contrast agent. And among all those paramagnetic species, gadolinium DTPA, which is agent actually first discovered in sharing the old days as an X-ray contrast agent, was become an outstanding candidate. In 1984, the first clinic result was published. As you can see here, this can be utilized to detecting tumor tissues. And a few years later, this agent was being approved for clinic use. And in the summary that the group of scientists in Schering nowadays, Bayer in Germany, they pointed out that the strong proton relaxation, in vivo stability, the rapid excretion, and high tolerance, and all those properties together make the gadolinium DTPA is most favorable candidate at that early days. Okay, and if I'm a chemist, so from a chemistry perspective, this is quite an obvious choice. And for the following reasons. First of all, of course, gadolinium is a lanthanide. You can get up to 7 unpaired electrons. And this is, of course, the maximum amount of electron that one element could ever hold. And gadolinium 3+ also has a quite suitable electron relaxation time, fits the Lamour frequency, and it has a quite larger size. And this is important because you need to stabilize the gadolinium naked ions using chelates. The gadolinium itself is toxic. On top of that, you also need to control the in vivo distribution, so-called pharmacokinetic behaviors of these reagents. So it is important that you have to create a very stable chelate complex. So a larger size, meaning that you can accept lots of coordination sites from those so-called multidentate amino polycarboxylate like the DTPA or DOTA here, and still leave a vacuum site for water coordination, and that water coordination, of course, can rapidly exchange with the bulk water. So this is, the larger size is in this sense is important to relate to the effexia as well as the safety. Okay, and those ligands are typically very polar. They have low lipophilicity. It does not interact with most of the biological macromolecules, and therefore they can be excreted very rapidly. And this is very important for the safety issue. So again, it's an early, obvious choice in the early days. It's an obvious choice, not only based on the discovery, but also based on the chemical science behind it. Okay, but nothing is really perfect. This is a principle that we all know as a scientist. And over the times that people start to recognize the limitation of gadolinium-based contrast agents. A typical clinic contrast agent has a relaxivity about around 4 millimole per second, but theories predicted that you can get easily, not easily, possibly up to more than 100 millimole per second. So there's a huge room to improve. Okay, and the other probably more urgent issue is that the relaxivity would rapidly drop, usually for those high relaxivity agents at high clinic field. And this is related to electron relaxation time and so on. And in order to optimize the effexity or the sensitivity or the relaxivity, more specifically, we have to optimize many molecular parameters. And these parameters including the distance between gadolinium and proton that bond water, the water exchange time, the rotation time, and electron relaxation time, and so on and so forth. And not to mention, there's also second sphere and out sphere relaxation mechanism, and which was beautifully summarized by the previous speakers. But this becomes very challenging because of those parameters, their interplay. They will restrict each other's. So it leads to a relatively narrow range for optimization. And sometimes the optimization could also lead to the influence on the safety. Okay, as I already mentioned, that free gadolinium is toxic. Even though like the DOTA or DTPA, you can achieve a very high thermodynamic stability constants. Kinetically, there's still labor. And that lability mainly in vivo is contributed through this called transmetallation reactions. In particular, the zinc ions could lead to exchange of the metal and leads to the release of the free gadolinium. And these free gadolinium could stay in vivo and could be detected actually even many years after the contrast agent being administered. So if you, for instance, increase the coordination site for water, increase the Q, then you would decrease, in principle, the stability. And the other things that we also need to keep in mind is and increasing the tumbling rates or increased molecular size often is a most popular strategy to increase the relaxivity. But increasing the molecular weight, the size, unavoidably would decrease the retention, the clearance rate. That means the contrast agent will stay in vivo for a longer time. And that could also, of course, lead to the risk of the in vivo metal dissociation. So all those things added together make the gadolinium optimization a very, very challenging task. And in particular, these days, we also wanted to, the entire field is aiming to develop molecular imaging agents that could target some biomarkers like larger molecules expressed on tumor cell surface. And this will require not only the high relaxivity, but also requires retention, longer retention time. And therefore, it seems a very difficult task. Over the past few decades, of course, we have many progress made, not only based on the gadolinium agents, but also increasingly gadolinium-free agents such as the manganese agents. And I'm showing you here, this is manganese agents called manganese DPTP, which was actually clinically approved, the only clinically approved manganese-based agent. But the optimization for gadolinium 3+ or manganese, in this case, is called manganese 2+ contrast agent. The challenge is similar. In order to achieve this really ideal contrast agent, which I listed all the criteria here. What would be the ideal contrast agent? We need high sensitivity, high relaxivity. In particular, we need to have a high relaxivity, keep it in the high field, kinetic field of 3 Tesla. And these need to be biocompatible. And as I mentioned already, the stability is really the key factor here. And on top of that, if we wanted to do molecular imaging, we need to have this called tunable pharmacokinetics. You need to balance the retention time and clearance time, and then you can also increase the molecular specificity by conjugating sometimes antibody and so on to do this kind of task. So as I mentioned, I want to stress it again that the manganese and gadolinium, manganese 2+ and gadolinium 3+ contrast agents, the sensitivity and stability, especially stability for manganese 2+ is very challenging issues. And this is because these agents, they are so-called half-full, F7 or D5, they are half-full. And the ligand metal interactions, the opto overlap are usually not as strong. Okay, so my group are interested in this class of compound called manganese porphyrin. It is based on manganese. However, this is a very different type of manganese. We have a manganese 3+. When you put manganese in porphyrin, it will be oxidized, turned into a 3+ oxidation state. So from a chemistry perspective, it's probably not the very best choice. First of all, you can only get up to 4+. In high spin manganese 3, you have 4 unpaired electrons. So that means we have a D4 electron configurations. As you may recall, that previous the speakers has been mentioned the theory, the classic relaxation theory, we pointed out that the relaxation time of this bonded water is linear proportional to the number of the spin times S+1, basically. So if you have a spin number of 4 in this case, or half of the 4 too, you would predict that manganese 3+, the relaxivity, that if everything else is similar situation, that the relaxivity manganese 2+ would significantly less than manganese 2+, which has 5 paired electrons. So 5 times 5 + 1, 6 is 30. Here, 4 with 4 times 5 is 20. For gadolinium, you have a 7 unpaired electrons, so you get a 56. So basically, manganese 3+, in ideal, even in the most ideal situation, you could maybe get 1/3 the relaxivity of gadolinium, and probably a manganese 2+ would have 1.5 times higher relaxivity. So it's not really the best choice or obvious choice from that sense. And manganese 3+ usually have a higher electron relaxation time. That still works okay, but it has much smaller size. By losing 1 valence electrons, manganese 3+, the ionic radius is significantly smaller than not only the gadolinium but also manganese 2+ complexes. And the further challenge comes from the porphyrin ligand. So as a ligand, as you can see here, there's a lot of aromatic, flat structure, which is used high lipophilic, low polarity. And for contrast agent, as we discussed, we need to be dissolved in water, need to be cleared quick. So this is also another challenge that has to be overcome. I want to give you a brief history of what has been done already in the manganese porphyrin-based contrast agent. So the first research was done in 1984, published by Chen and others. They recognized that manganese, water-soluble manganese porphyrin derivative, in this case called TPPS, which is 4-sulfonate on attached to the phenyl rings. This water-soluble agent exhibits somewhat surprisingly higher relaxivity. And this study was later also continued by Samuel Koenig. And of course, you can recognize that porphyrin is a analog. The synthetic porphyrin is an analog of natural heme. So people also evaluated the heme derivative of a different type of the heme derivative, the manganese derivative, and evaluated them as MRI contrast agents. And later on, more synthetic people come in and tested also a range of other synthetic water-soluble manganese porphyrin. And even people conjugate the porphyrin with gadolinium agent. And the reason of the interest in the early days are mostly focused on the tumor targeting ability of the porphyrin, because as some of you may know that porphyrin is actually a class of therapeutic agent for tumors based on so-called photodynamic therapy. Porphyrin can be selectively uptake by tumor cells, and so this will lead to a selective therapeutic ability for based on that therapeutic purposes. And people could think that, of course, then if these contrast agents can selectively uptake by tumor, then we have a very tumor selective contrast agent. But the issue was actually, in order to have a selective tumor targeted imaging, you need to have a relatively high dose, but the porphyrin derivative, such as the MnP-Based BPAs, has a relatively high LD50 values. The toxicity is relatively high, and you require a high dose. And in some of the early clinic, the animal studies also found out that the animals, the skin get colored by the porphyrin, and that means the porphyrin is also distributed and retained on the skin. So this is the state of the art. When we started our project, so our idea was looking back all the porphyrin that I've listed here. These agents has lots of in my view, unnecessary substitutions on the porphyrin, either on the meso positions. This is a meso position. These are mostly synthetic derivative, has meso aromatics. The nature substrates, often they have this aliphatic on the so-called beta position. And those substitution, aliphatic substitution, are really not necessary. For tumor imaging, maybe they will be very important for selective tumor uptake. But if we take off all those, eliminate all those agents, we could actually come up with a very small and polar porphyrin derivative, and these derivatives may not be able to uptake by the tumor cells, but they will probably behave similar as a manganese, as gadolinium derivatives. They will stay outside of the cells, and they will go to extracellular spaces, and they could rapidly so-called extravasation, and that would ability leads to detection actually of the tumor by dynamic contrast enhancement. And that could also, of course, lead to improve the safety, since you do not have interaction with the tumor cells, and the minimum chemical interaction would lead to a better tolerance. Okay, and in terms of the application, we will be using this agent, the polar agent, same way as the extracellular gadolinium, which has demonstrated already in the clinic studies. But of course, one of the key questions is, will you be able to keep the relaxivity? And we believe that even though this compound is much smaller than those synthetic or nature porphyrin derivative, but when we introduce the carboxylate in the peripheral, this will increase the water accessibility, maybe will influence the ousphere relaxivity, and we might have a good chance that to have a remain a high relaxivity. And my first PhD students, Charles Inga, she's very talented synthetic chemist. She was able to make this compound in just a few steps as shown here. I'm not going to go into details, but porphyrin compound, unlike the gadolinium, has very rich optical properties. We can detect them by UV vis and monitor the reaction, monitor the purity, and so on. So we were able to make these compounds with a reasonable yield, relatively high for other people, because porphyrin synthesis one step actually make it such a complex ring. So the yield is relatively low, but a very acceptable yield. And we went further. We measured the sensitivity by, of course, a field-dependent relaxometry. So at the early days, we don't have our own instruments, so our collaborators at Western, Tim Scholes, helped us to measure this, obtained the NMRD, and we compared it in the body with manganese TCP with gadolinium DTP. Immediately, as you can see here, manganese TCP has a stronger, higher relaxivity, not only at low field, but particularly at high field. And 1 Tesla, the relaxivity is more than 2 times stronger than the gadolinium DTPA. But the challenge comes at the point when we try to fit data with the classic SPM model. We have to use somewhat physically unrealistic parameters. For instance, One possible fit would be have to use a very short, this so-called hydrogen to manganese distance. And this is, of course, doesn't seem fits the reality. The distance must be longer than that. So a quick literature surveys will give us all these necessary parameters that would relate to the explanation of the relaxivity behavior. For instance, and this is another interesting thing for porphyrin chemistry, because there's a lot of other people interested in manganese porphyrin, not for MRI purpose, but for catalysis or understanding how natures of the porphyrins or hemes on oxygen activation, binding, and so on, or photodynamic therapy. So there's a lot of chemistry that we could actually learn from. So it turns out there are a number of manganese porphyrin, not water soluble though, not made for MRI, and the X-ray structure was published. So based on the X-ray structure, you can see that these manganese porphyrin could easily adopt 2 water binding site. And this is manganese TPPS. The structure was obtained not from water, but there's a 2 water coordinated if you add a little water in the system. And you can, based on the structure, of course, you can look at what is the hydrogen distance to the manganese. It's statistically, it's all within about 2.7 to 2.9 Armstrong, which is, of course, a little bit shorter than gadolinium, but not huge difference. And the water exchange rate were also measured, actually, for other purposes. There's other different types of manganese porphyrin, even including the manganese TPPS. And this was published in 2010. And the range of the tau m, or the residence time, is within tens to hundreds nanoseconds, which is quite reasonable as obtained by the oxygen 17 NMR. The tau r, on the other hand, there's not a lot of reports on this, but we can estimate them, for instance, through molecular modelings, and there's nice models for if the compound can be viewed as a spheric, you can estimate the tumbling rate using this equation. And you can also potentially measure the tumbling rate of the porphyrins through fluorescent polarizations. And this is another interesting properties of the porphyrin, because if you don't put manganese, if you put something, if there's no metals or put diamagnetic metals, the porphyrin are often fluorescent. So you can use the fluorescent polarization method to determine the tumbling rate. Okay, and because the tumbling rate plays such an important role in gadolinium, so we try to explore that, tune that parameters and see if that could lead to the influence of the further improve the relaxivity. So I showed you that we try to minimize the porphyrin structure, but here in this case we do the other side. We increase the size of the porphyrin by forming a dimer, a conjugated dimer, through this pi-pi conjugation chemistry, and we would expect that this will slow down the tumbling rate and therefore leads to the increase of the relaxivity. Again, I will not go to the details of these synthesis, but we made this compound through a palladium catalyzed homolytic conjugation method based on borate derivative. And so we made this compound, and if you now compare the relaxivity of this manganese linear dimer, as you can see here, as we predicted, the relaxivity drastically increased at high field. So per manganese, not per molecule, but per manganese. So the relaxivity at 1 Tesla reached almost about 20 per millimole per second. And if you compare the size of these porphyrin, this is manganese TPPS, which was previously studied by other people. And we have also manganese TPPS, which is a new compound designed by us. So the size correlates quite well with predicted relaxivity. So this is something very similar as gadolinium complex. And interestingly, we also studied the geometry of those compounds. For instance, the dimer here, which I showed you, has a so-called para-dimer. And this is yet another interesting property, because the porphyrin, they are aromatic. So there's not a lot of flexibility for those kind of sigma bond rotation. There's only limited restrictions, rotations, freedoms. So for this linear dimer, the only way to rotate is through this sigma bond here. And this sigma bond rotation actually does not change the diameters the size of the porphyrin. So the porphyrin, you can estimate the diameter is roughly about 3.5 nanometers. But if you change the conjugation, not at the para, but at the meta position, in this case, this single bond rotation will change somehow the size of the porphyrin. And this porphyrin is kind of like a tunable structure based on this rotation. And we could estimate the range of this, the size is between 2.3 to 3.3 nanometers. And this tiny change actually did has a clear impact on the relaxivity as we predicted, because this is make this a relatively small diameters, and you see that the relaxivity indeed also decrease. So very interesting, but is what we predicted. The other things I didn't mention, that the reason we're interested in this kind of diphenyl rings in the middle is because we want to develop blood pool agents and to let it attach to the serum albumin, which we'll mention later on. Okay, the 3 Tesla relaxivity can be measured, through the phantom imaging using the clinic MRI scanners, and from that studies we could clearly see that the contrast agent, the higher relaxivity, will indeed turn into a much brighter spots. And we also measured the T2s based on the imaging analysis. As you can see, the T2, TR1 to R2 ratios for manganese porphyrin is quite close to gadolinium. Here, TCP is about 1.15, and for the MnP2, the larger diameter is about 1.3. And if you compare this R2, R1 ratios, for those of you not that familiar with this, the R2 is the so-called T2 relaxation time often leads to the darkness of the signal. So the larger the value is, often it's compromised signal intensity. So we want to have minimized R2 to R1 ratios. So this R1, this ratios for manganese porphyrin is quite actually ideal or acceptable. Of course, these values doesn't really explain why the manganese porphyrin has such an interesting or unexpected, unusual high relaxivity. So it turns out that the reason we cannot use the SBM, the classic SBM model, is because the SBM model has a very important assumption that is based on the so-called dipole, point dipole, structure assumption, meaning that the unpaired electron really has to be localized, sitting in the paramagnetic centers. And that works very well, of course, for gadolinium and or manganese 2+, because these agents, as I mentioned, they're half-filled electron configuration. Their electron crowd is kind of spherically symmetric. But that dipole assumption will become almost invalid for the manganese porphyrin. And this is because now we have actually D4 electron configuration with the octal, one of the octal is empty. So by analyzing the molecular octal, we recognize, or others as well, as pointed out by Samuel Koenig in the early days, and these electron configuration actually quite favors the interaction with the water. So for instance, the highest occupied, singly occupied octal of here, with the last electron would have come to the DZ octal, which is really perfectly aligned with where the water is bonding, and of course that would leads a much shorter the distance. And for those of you familiar with the theory, we know that this R distance is actually power to the 6 that could influence the relaxivity in a very drastic manner. And furthermore, because of electron relaxations for manganese porphyrin is relatively faster than gadolinium and manganese, that could also potentially favors the relaxivity, in particular at the high field, when the electron relaxation is, by the way, field dependent. At high field, this electron relaxation will slow down. Robert Sharper, his group actually further studied this in more details. He pointed out that the zero field splitting pattern, in particular this so-called fourth order components, which is shown here in this slide, which splits the octal between x squared minus y squared to xy. And this plays a very important role in the electron relaxation. And that the zero field splitting tensors actually is coupled with the molecular tumbling rate. So he was able to explain why these the behavior of these contrast regions. And on top of that, these two explanation still, I think, need some more confirmation or experimental validations. There's also other elements that's not being considered, and that has to relate. It has come from the interaction between the strong interaction between the metal center and the porphyrin ligands. I didn't explain to you why, when you put the manganese into the porphyrin, it will become oxidized. From the superficial levels, you can extend it through the sides, because the porphyrin is a very flat, rigid coordination environment. If you have a manganese 2+, you have the diameters is about 97 picometers, which would not sit perfectly well inside the porphyrin. When it is oxidized to 3+, by losing one valence electrons, becomes smaller, and the porphyrin wall fits much better in the rings. Okay, and that, of course, size fits would leads to the stronger orbital overlap. The stronger orbital overlap can somehow already observed by the UV vis. Typical porphyrin, like the apoporphyrin or metal-free porphyrin, you will see something we call the Q-band. A strong Q-band will come from the pi-to-pi star transitions due to the porphyrin pi electrons. When you insert the manganese 3 in this case, this Q-band will split. And that is really strongly indicates that the interaction between the pi electrons of the porphyrin and the metal centers. And that, of course, could now strongly, this optical overlap would greatly stabilize the manganese 3+ complex, and that would now stabilize the structure now, even with just 4 nitrogen coordinations. And this leads to, of course, 2 water coordination can be rapidly exchanged. And the interaction could also be proposed that could lead to the spin delocalization. And the spin delocalization means the spins on the porphyrin could exchange, or the electrons in the porphyrin could exchange with the manganese spins, and that could shorter the electron proton distance. So here we no more talk about distance between manganese and hydrogen, but really the key is the distance from hydrogen to the unpaired electrons. So if the spin goes into nitrogen a little bit, and then you will see that distance, of course, will become shorter. On the other hand, the spin polarization, there's some mechanism called spin polarization mechanism. For instance, an electron can be given from a porphyrin rings to manganese 3 center to get kind of a pseudo manganese 2+ configuration, and that could lead to now 5 spins on manganese, but the porphyrin will have something like a cation radical, and that could further increase the effective spin populations on the rings, and further on, and these delocalized spins on porphyrin may possibly enhance also the second sphere relaxivity or outsphere relaxivity, if you will. But those are the hypotheses, to be honest. We don't have really a strong evidence on this, and this is the reason I'm so excited. I hope that the colleagues, I'm a synthetic chemist, I really hope that people have a deeper understanding of the series, and the audience will come up with more interesting models and help us in understanding these more quantitative understanding of these values. We did a little bit of DFT calculation. As you can see here, the spin population, indeed, as we predicted, is delocalized. Now the spin is not only on the manganese, but also goes through the porphyrin. When you see not only the one side of spin or positive spin, you also see both alpha and beta spin. And interestingly, one of the spins, a little bit of spin, actually even goes into the water, and that, as you will see, of course, could really significantly increase the relaxivity. But there's still lots of questions unanswered, and we need much more theoretical or experimental efforts to understand these behaviors. As I mentioned, these strong interactions will lead to the strong stability, which is relatively easy to be measured. As I already mentioned, the porphyrin has a very unique UV vis. Manganese porphyrin has a unique UV vis, very different from the metal-free or other paramagnetic metals. So if there's a metal dissociation or the metal is exchanged with other things, we should be easily detect these changed by UV vis. So my students, Keith Tang and the previous students, Henry Tell, so they spent some of the efforts monitoring the metal exchange or the challenging the stability of the manganese by adding acid or by adding other metal species in the solutions. As you can see here, the system is remarkably stable. So over the course of even several months, we never able to see the metal dissociation even decrease the pH or adding excessive the manganese or raise the temperature. So this really confirms that these strong metal-ligand interaction indeed results in very stable, high stability. And this, of course, is a highly favorable property, which is what we are looking for: high relaxivity and high stability. So now I wanted to talk a little bit more on the application side. So as I told you that we designed the manganese TCP, the smallest one. We wanted to have that agent for very fast clearance and detecting tumors. And indeed, the animal study really showed us that when you inject these agents, very quickly the agent will pass through the kidney filtration and will accumulate in the bladders. In 1 day, all the signal enhancement is gone, meaning that the agent is excreted very efficiently. Very similar behavior as gadolinium, but if you look at the parents compounds, the manganese TPPS, after 1 day, you can still see some of the retention in the liver as well as in the kidney. So our structures modification did work very well, and we can further confirm this by collecting the urine samples. And as you can see, easily by eyes, because porphyrin are deeply colored. So collected urine, you can see the porphyrin colors clearly in the urine sample. So from here, you can, of course, not only quantify how much porphyrin is excreted, you can also look at the structure changes of this, and indeed these porphyrin remain bonded with the manganese, and there's no structure alterations during the in vivo filtration. The tumor model also works very well as we predicted. So we inject this. So this is the in vivo tumor models. So gadolinium could detect this enhancement of the signal, and this is due to the the leakage of the local vascular, increased vascularity and the leakage of vascular structures. Manganese TCP at the same dose, you can easily detect that, but of course with a higher signal intensity, which is due to the high relaxivity. We could also use a detector to bring tumors, which is of course the gold standard for clinic diagnosis. So this is the tumors that the tumor model created by metastasis from a colleague from Western University. As you can see, the manganese could very quickly pick up these tumor models very reliably. I also wanted to talk a little bit more on the other type of application, which is to image not just the extracellular but intracellular space. As we know that most of the liquid is really sitting in the extracellular space, but there's also a really large amounts of the intracellular volumes that lots of biological, or pathological events is happening inside the cells. We need somewhat detect what happens inside the cells by MRI. And in particular, there's a field so-called cell labeling, cell checking, which is required for instance, to monitor those therapeutic cells such as stem cell, immune cells. Those cells, when they're injected in vivo, often people would lose the ability to visualize them, whether they're still alive or they've reached the targets. So the idea is to label those therapeutic cells by contrast agents, and often this can be done by T2 agent, which is, as I mentioned, is an active agent. You leave the darkness. This is not the best, most acceptable method for clinic uses. The clinician would rather see more unambiguous brightness of the signal, because darkness could caused by other things such as gas bubbles or inhomogeneous tissues, things like that. People also use fluorine-based agents, but the most clinically accepted T1 agent wasn't very successful for that purpose. And the reason is the following. We need, in order to label the cells, you have to cross cell membranes. And as I mentioned to you already, the classic gadolinium agents, of course, you have to use a very polar, low lipophilic ligand complex, and therefore it cannot cross the cells more freely. On top of that, if you deliver into the cells, then the gadolinium, you may have to worry about the toxicity issues because of the longer retention inside the cells. Okay, and manganese-porphyrin may be able to do a better job because it's more stable, and of course manganese also is more biocompatible. The question is, now we have this highly polar compound, would we be able to convert it to a cell permeable version? So we use this concept called prodrugs, which can convert this polar carboxylate group into an ester form. And this ester form, called AM ester form, is now neutral or more lipophilic, and therefore it could now cleave, pass through the membranes more freely, and then it will enter into the cells. And those AM esters could be hydrolyzed by an enzyme called esterase, intracellular esterase, which is can be found almost in any cells, and that would release the active form, the manganese TCP, which we know has highly active in MI. And because this is now negatively charged, so the TCP form, once being hydrolyzed inside the cell, cannot escape, and they will be trapped and enriched further in the cells, and therefore it will lead to the higher cell loading or stronger labeling. So as we predicted, when we made this, the lipid form, these agents, because it's now lipophilic, has a much lower water solubility, and therefore it aggregates. You can monitor the aggregates by dynamic light scattering methods, and you can see the average size would increase over time. The UV vis also drops, and more importantly, because of the low solubility aggregation, the relaxivity also significantly drops in this the ester form. Once you introduce the enzyme, the esterase, in the solution, you see that the agent will be activated, become more water soluble, and therefore the UV vis will back increase. And you can also detect beautifully these hydrolysis by HPLC, of course. These will change drastically the retention time. You can see this intermediate formed one by one over time. And most importantly, when these are hydrolyzed, of course, the relaxivity will also getting back, the T1 will become shorter. And as we predicted, that these agents, when you incubate them with the cells, it could enter cell very efficiently. You can see it already by your eyes. And that also leads to stronger T1 enhancement. And if you quantify this value, this shortening of the T1 is actually the most effective one and so far. So manganese AMP could lead to the decrease of T1 from 1 second at 3 Tesla all the way to below 200 milliseconds, microseconds. And then in 1 Tesla, can see something that's even more significant in this case. And so the manganese AMP is so far the most efficient T1 agent for cell labeling. And more importantly, these labeling cells doesn't change too much the cell proliferation rate, so the toxicity is quite low, or it's quite biocompatible. We also open up the cells by using these saponins, which can poke holes in the cell membranes, and you can extract this porphyrin outside, and we can also compare where it is localized by comparing the MRI as well as the UV vis or manganese atomic absorption, and we could see that most of the porphyrin is actually accumulated in the cytosol, does not associate with membrane or does not go to the nuclear as we predicted. So this is actually the reason why it can keep it not toxic, because it does not interact with too much with the with other cell compartment. This is at least our hypothesis, and we also use this to label the stem cells. And importantly, the stem cell not only get higher T1 signal, but the stem cell can keep alive and function, and eventually, in this case, my colleagues Margaret Chang showed that this stem cell can also turn into a beating heart cells. So this is demonstrating that it's really biocompatible. And next, I will talk a little bit about the angiography technique using Mn-Porphyrin. So MRA is a technique to visualize the vascular structures in the human bodies. In order to do that, of course, we have to keep the contrast agent circulating only inside the blood vessel, not going out. Okay, so we require a contrast agent that now will be should be much bigger, because these classic small extracellular agents, they're too small, so it will leak throughout the cells. So this leads to the new class of contrast agents that people developed already use gadolinium, called blood pool agents, and often we have to increase the molecular size, or you can use a conjugation or non-covalent interaction with a protein sitting in the blood. But nevertheless, to be an ideal blood pool agent will requires longer vascular retention. So you have to circulating what's going out, and therefore you leads to a long in vivo retention. And then, as we mentioned already, that would potentially leads to the gadolinium leakage if it is not very stable. So this again will be the advantage for manganese-porphyrin because it's so stable. And the agents we tested this for MRI is the MnP2, as I discussed earlier, which has a dimer that has a biphenyl group in the middle. This biphenyl group is known to form a non-covalent interaction with a blood pool, and with a protein sits in the blood called human serum albumin. And so we test that and compare this with a commercial compound, MS-235, or called Abravar, as the commercial name. And we measure the relaxivity of these, our manganese-porphyrin, as comparison with the Abravar. As you can see, the Abravar, upon the binding of the human serum albumin, has drastic increase of the relaxivity. However, the relaxivity really peaks below the clinic field, 1 Tesla, and it will sharply decrease over as the field increase. In our case, the manganese-porphyrin would have higher relaxivity, at high field, and it would decrease, but not as drastic. So at 3 Tesla, the high clinic field, as you can see here, the manganese-porphyrin is actually has a significant higher sensitivity than the Visovast or Abravar. And this is per molecular, so still per manganese, manganese-porphyrin, this level is still slightly higher than the Abravar. This stronger interaction with the human cellular albumin also leads to expected longer vascular retention, as you can see here now. The MnP2 after injections will highlights the hard vascular structures, and 60 minutes you still see a very significant increase. So we can follow those retentions by longitudinal MRI. As you can see here, even after 1 day, the MnP2 still has a very significant enhancement in the blood. So the retention time is very long, excretion time is quite short. So we use this, my colleague, my collaborator, Margaret, used this agent also to imaging the lungs, as you may know, that the lung is actually a very challenging organs for MRI, because there's a lot of air, so often you see a black holes, and MRI would be very hard to detect this. And because of MnP2 has a such stronger vascular enhancement, so using this so-called ultra short pulse sequence, Margaret was able to image the blood flows in the lung. And this is one kind of interesting applications. The disadvantage, if I may, that for this dimer manganese-porphyrin is upon the binding to the HSA, actually relaxivity significantly drops, and this is very different for gadolinium agents. We still don't know why this happens. And on the other side, if you wanted to optimize it, that we feel like the retention time in the vascular system is too long. Because once you finish the imaging, you still want these agents to be excreted. So if there's a way that we can tune that retention time, depends on what you needed for the study, we hope that we could achieve a serious compound as a control retention time. And if you needed to the MRI done very quick, use a quick excreting, but if you need long time, then you will use MnP2. So to understand or to design a better agent, the question is how does it bind to the HSA, and with this binding behavior could be used to tune for the pharmacokinetics. So my student Haling, he's probably sitting in the audience today. He was using the a lot of optical method to study these bindings. He very elegantly he's using this metal-free versions of the MnP2 dimers, which actually shows a very interesting CD spectrums upon the binding to the HSA. But what was really surprising us is that the binding of the this dimers with HSA shows a kind of biphasic or multiphysics. At times you see the signals first have a positive and then negative, but over time this positive negative switch to a negative positive. And same behavior could also be observed by UV vis, even though the change is small, but we can actually plot this changes. You see that goes down, UV vis absorption goes down and then goes up. And this of course encouraged Haling to look at the manganese derivative as well, and you see a similar UV vis absorption. Then we monitor the binding behaviors by relaxivity. The relaxivity actually drops over time, and if you pay attention to these time scales, actually it drops very slowly over time, or these changes happen very slowly over time. And this slow changes could also be observed by the colorimetric titrations, ITC method. You see that usually the binding events for ITC you see a really sharp peak, but in this case you see a very broad peak, indicating the slow processes. So we hypothesize that this porphyrin binds to HSA through probably a multiphasic or multiphase stage. You have a kinetic binding phase, which is very quick. Binding will happen on the surface, but over the time, the protein will try to put the porphyrins in a much deeper binding pocket. And we identify this pocket is actually called site 1B, which is now increasingly studied these days as the so-called third binding pocket. It's not located in the classic binding pockets called cellular site 1 or cellular site 2, which is defined by the classic drug binding analysis. And this is quite interesting that it's the first time that we discover this. There's a two-step of the bindings, but it's really this two-step binding is only for MnP2, or it's actually natural functions, and we believe this is probably related to this natural functions of this. But anyhow, for our relaxivity, the reason we see such a decrease now can be somewhat explained, we believe now, because of the binding goes much deeper hydrophobic site, and that could restrict water binding because the water cannot go these hydrophobic site anymore, or at least not that freely. So we designed a new contrast agents, and so having synthesized this new agent, we normally have the dimer, we have the carboxylate. Again, you can see that these elements from a small manganese TCP, and we only have a one hydrophobic site, and we hope that this hydrophobic site would binding to not a deep pocket, and these carboxylate will keep this porphyrin is more accessible to the water. And as we predicted, these agents indeed now upon the binding to the cellular albumin, not decrease the relaxivity, but instead drastically increase that relaxivity. So in a way, this binding can be tuned. And we also try to, of course, attach these porphyrins as we discussed earlier. The longer term goal, at least the big goals for the field, is try to get molecular imaging. And one of the obvious ways is to covalent tag these porphyrins on antibody or some other agents. And so we studied the covalent interactions of those isocyanate derivative, the porphyrin. And the beauty is porphyrin, again, as I mentioned, that you can make a metal-free, which is fluorescent. So we tested in the cellular albumin, which of course is commercially available and has a lot of license on the surface, could react with the isocyanate to have a multiple tag on surface. We can characterize the product by MS, and we run the gels, and you can see we derivatize them both on the manganese version or the fluorescent versions. And these different derivative shows interestingly a different retention time, and that is probably due to the charge on the manganese. But very interestingly, Now we can visualize these gels either by MRI, because this is the manganese version, or by fluorescence, because this is a free fluorescent versions, and the relaxivity also increase upon conjugation, because there's some subtle increase of the tumbling rate. But this tumbling rate, of course, there's also free motions, intermolecular motions, so it's not as drastic as the dimers. We could use this fluorescence imaging to visualize how much or where it's localized on the cells. The fluorescence is more sensitive than the MRI. When we look at the MRI cell labeling, and we didn't see as a strong relaxivity, but a strong signal as a fluorescence, but we did see clear enough decrease of the T1 time measured by relaxivity. And this decreased T1 time, even though not ready for MRI imaging, but we believe will give us a really clear signal, that information that we know now how many porphyrin we need to put on the antibody. And with this, I think I'm more optimistic than before. I think that molecular imaging with MRI tech is very possible in the future, and we are still working on that. So this leads me to the summary. I hope I've showed you already what soluble manganese porphyrin is an interesting candidate for next generation MRI contrasting. Not only it shows a high unusual relaxivity, but it's also very high stable, and all those is because of the strong metal-ligand interactions. But that, of course, raised the challenges that the classic relaxation model cannot really quantitatively explain those behavior. We need more modeling or more experimental evidence to prove our hypothesis, and hope that more colleagues will join us or collaborate or other format. And I will be happy to talk to you on this. But the advantage of those could be utilized through the structure modification of the porphyrin by introducing different R groups, and this would allow us to not only create this extracellular agent, but also make this is the tumor agent, which I don't have time to talk about, but cell labeling agent, as well as a blood pool or covalent tags for future targeted imaging. So this is my last slide. I'm sorry for the overtime. I wanted to acknowledge all the collaborators in the past. I don't have time to read the name out. The previous group members, as well as the current group members. This is old image definitely before COVID. I need to, of course, probably update this picture. And with this, I want to thank you all for your attention, and I'll be happy to take questions.
Thank you very much. This was impressive, really. And I have to say,